Usually you're being live streamed. So good morning, everyone. I hope the times have changed today. So that didn't cause too much consternation. I, in fact, had forgotten about it. So I woke up a bit later than I should have. So there you go. All right. So today we have the following agenda. This is our lesson plan. We are going to transition from doing what we have been doing, namely RAG up to now. If you remember, we left off doing RAG, retrieval augmented generation. So today we're going to enhance RAG or go much further by bringing in not just text, but also, guys, please mute yourself.
Once you've done that, you have to talk to them and make time. You have to talk to them and say, hey, I want to advance my career.
Irfan, please mute yourself. Yeah. All right. So, so today we are going to go into a very exciting area of work in neural networks. I mean, AI. In fact, I would argue perhaps the hottest area of AI at this moment. Can you guess what that area could be? Video. Well, we are doing this whole bootcamp is large language models. So it is certainly the hottest area of activity using transformers. But within the space itself, it turns out that the one area that has really caught fire in the last 2-3 years has been multimodal learning. How can you take all of this together and synthesize it? So we'll talk a little bit about that. Right? Any questions, guys, before we go into RAG, before we walk away from RAG and so forth? So in the morning, we are going to do multimodal learning. We are going to cover 2 papers. One is on vision transformers, and the other is an introduction to perhaps the first multimodal approach that became very popular, called CLIP. So we'll use CLIP and vision transformers as a launch pad into this new field of multimodal learning. In the afternoon, what I'm going to do is walk through your projects. I realized, talking to some of you, that not much progress has happened. Like, people have worked on patches of the project. So what I will do is I've uploaded partial solution, which actually is hardly partial, it's practically the whole solution, to the first project. But this is not a harbinger of things to come. For your subsequent projects, you won't get such detail of practically the whole solution. The point is that you should try on your own. Now, some of you have been trying really hard. I notice, I hear and I know that some of you have been staying up till very late nights, till 2 in the nights doing your projects. Really admirable. And you have made great strides with it. So compare your solutions to what I'm going to show and build upon it using that. So that's a plan for today. It's a very simple plan, an introduction to multimodal learning. We'll do 2 research papers, and then in the afternoon, we are going to do a code walkthrough. And then after the code walkthrough, you will probably take a couple of quizzes on the portal. Now, a couple of words on the portal. As you know, the portal had gone down after, like, it was the first time in 8 years that we had gotten hacked. We have restored it, but the restoration is not quite complete. At this moment, it has 2 singular absences. One is the videos are not showing up on time, and in fact, many videos are missing from our sessions. I'm in a catch-up mode. I just came back yesterday night, and with some luck, this week we would have caught up on the videos. The second thing is there are insufficient quizzes and other self-assessment tools on the portal at this moment. And so we have to fire up the AI engine to start doing it. We usually fire up the AI engine as the last step so that it doesn't miss anything. We should be there with some luck. All of those things should be achieved in the earlier part of this week itself, or certainly by end of this week. So by the time we meet next time, you will see everything in place. So those are the two remediations needed in the portal, and I apologize for the delay that it has taken. Now, with that being there, I am getting echoes. With that being there, let's get started. So once again, a lot of people have just stepped in as we started speaking. Welcome again to today morning session. Today is our day 4. We are going to transition into a very important topic, multimodal learning. But before we do that, we will first take one more modality, namely vision, and add it to our arsenal of, for example, the things that we are able to do with transformers. So this paper is about that. It extends the use of transformers to images. But before we do that, I would like to go back and spend about a little bit of time recapping CNNs. Now, how many of you know what CNNs are? Convolutional neural network. Most of you have raised your hands. Those of you who haven't, what I'll do is you will encounter, I hope you are there in the Tuesday's class, because we are going to do convolutional neural networks in great detail. Today, because this course is devoted to transformers and large language models, we won't have time to study the convolutional networks from first principles. But I'm going to give you a very simple intuition about what it is and what its salient features are. So this first session, consider it, the first hour, will be a short, less than an hour, would be a short recap of how convolutional filters work. Right? So before we ask convolutional filters, how were they discovered? They were discovered actually in a very interesting way. People looked at the standard neural network, the multi-layer perceptron. Do we know what multi-layer perceptron is, guys? Just feed-forward networks, lots of neurons feeding into the next set of neurons, feeding into the next. So for example, what you just did in the homework in the other class was a multi-layer perceptron. Right? MLP. So the words MLP, feed-forward networks, dense networks, linear networks, etc., they're often, they're sort of more or less synonyms. And people tend to use that quite a bit in the literature. So let's stick with MLP for short. And when I mean MLP, it is just a network made out of neurons, dense layers, interconnected to each other. So suppose you take a layer that has, let's say, 1,000, and I'll start writing now, 1,000 neurons, which is relatively not, well, it's a little bit larger, even 512, it doesn't matter, neurons that you have built in. So let's do that. Let's say that you have one layer. Actually, one thing I can do, I apologize for this. I got a request from the audience if I could change the color, because is the glare still happening, guys, or no more? All right, let's try a look with that. All right, so let's say that you have a layer that has, I'll just choose the word n, where n, say, is, let's take 1024 neurons. Are we together? And this is our layer 1. It feeds into another layer, layer 2, and then it feeds into subsequent layers. So suppose you have up to layer k, and you may have different. For example, this may have M number of neurons in it, M number of neurons, and you can keep going on. Are we together? Right? Or why don't we use a standard notation, N1, N2 to Nk, number of neurons in this feed forward network. Or so again, these words are interchangeable. Feed forward network. Why are they called feed forward network? Because the outputs of the one layer feeds in as the input to the next layer. Are we seeing that, guys? Right. And therefore, the terminology feed forward networks. Now, it is also called multi-layer perceptron, multi-layer perceptron, MLP. Why is this terminology together? We literally see K layers, isn't it? There are multiple layers, or layers made up of what? Neurons. Or one of the words that was often used for neurons, or a synonym for a neuron, is a perceptron. So this word especially dates back decades, perceptron. Right? You will also see sometimes literature talk about dense layers, which means the same thing, right? A dense network, a dense layer network, or something like that. So let's think about it. How many weights are involved here? In this region, how many weights do you think are required in this region? So each node I connects to, if you look at this, each node I connects to how many?
N2.
N2. And how many nodes are there in the first layer? N1. So what is the total number of interconnects?
N1 and N2.
N1. So total interconnects are times N2, isn't it? And how many interconnects are there in the second layer, between the second and the third layer? N3 plus Nk minus 1 times Nk. Does that make sense? So the total number of interconnects is this much. These are just the weights. We are skipping the biases. Right? Now, if you look at this and you ballpark it, you realize that suppose, just for simplicity, suppose I took 1,000, I took 5 layers of 1,000. How many parameters would I have in my model?
5 million.
5 million. Why? Because you would have 1,000, which is 10 to the 3 times 10 to the 3, and 5 times over, isn't it? So you would have 5 million, give or take, neurons in your network. I mean, sorry, weights in your network, parameters. And those are just the weights. But then there would be also biases, right? So biases, relatively speaking, will not be that many. There will be N1. How many biases will there be? Literally, N biases would be. So these many weights. Yes, there will be, literally N1 plus N2, Nk. In our particular case, it will be 1024 times 5, right? Give or take 5,000. Does that make sense? So that is a relatively, I mean, when you try to solve a problem, you realize that there are way too many weights out here. Go ahead, your question.
How come the weights also should be in same weight? How do you
No, see, look at this. Every neuron, ith neuron in the first layer, connects to how many neurons in the second layer? N2. And every single neuron in this layer does the same thing. Right? So how many total bridges are there between neurons of this layer and the neurons of the next layer? First and the second layer. And one into it. Exactly.
So, yeah, so that I got it. Even find the weights I got it.
No, because each of the bridges has its weight attached, right?
Yeah.
So there is a weight attached for each of these. And that explains it. Does that? Because see, every bridge has a weight attached. Every edge has a weight attached to it. Yeah, and each edge has a weight attached to it. So how many weights are there? Exactly. That is it. All right, guys. So you realize that this is this sort of system. When you see so many parameters, well, these days we're talking parameters in very large numbers. Prashant, you have a question?
I think hypothetically we know that these are weights, but how do we get those weights?
Oh, you through back propagation, through training. Remember the whole thing that we learned, gradient descent, back propagation, that whole learning loop. That is it. So, that's a good segue actually to the point that I'm making. When you have these many parameters, you need to know the right value of each of these parameters for whatever downstream task you're doing. Let us say that the task is classification. Then for classification, at the end of it, you're feeding it into, let's say, a softmax or a sigmoid function that will do your classification, isn't it? And you need to, whatever the loss is, whatever the gap between, in the training data, the gap between prediction and label is, you need to backpropagate. But when you have so many parameters, what's your basic intuition? How much data do you need to train this? A whole lot of data, isn't it? Otherwise, this machine, well, the basic intuition from coming from classical statistical learning would be that it runs the risk of overfitting. Now, having said that, I must also say that today we know that overfit with neural networks are a bit strange. They have the phenomenon of double dip. They're a little bit more robust to overfitting than traditional machine learning algorithms. So, but having said that, let's go along with the narrative that it's a whole lot of data needed to train this network. So it's not data efficient. You have to do a lot of back propagations, a lot of cycles and epochs to get this neural network trained. So the question that people ask is that, can we create much more efficient neural networks? And in the pursuit of more efficient neural networks, the question was, how do you sparsify it? Right. There are many attempts, but one attempt in particular that really took the world by storm a few decades ago came actually from neuroscience or neurobiology. People were looking into how cats see, and they were looking at the receptive field of the cat. Like, for example, if something here moves, as you know, the image of something, it is a very simplified and a non-biological, semi-biological way of thinking about it is that, imagine that at the back of your head, there is a screen, a projector, right? And so I don't know if you do this little experiments. I used to do that as a kid. If you ever take a lens and you look at the outside world, what happens here? And you have a wall here. What do you see on the wall? You will see, right? You would see an image of that. So this becomes this, and this becomes this. It goes there, isn't it? But if you observe, because spatially, that what you see in the external world is preserved. Now, one of the things that they observe is that the activation of the neurons in the cat's brain were very local to what it was seeing. So imagine that ahead of it, or this whole screen is actually made up of receptors. So you would agree that the receptive field that is associated with just the leaves would be a localized receptive field, isn't it? The leaves are being observed only by the neurons that are, I mean, if you think of a layer of neurons in the cat's brain effectively as the projector that's responding to that image. Does that make sense, guys? Is the intuition clear? Right? It is exactly the way your digital camera works. How does it work? You have a lens, and in mammals, you have the eyes, or in even fishes, you have the eyes. Right? Now, in a camera, it's again a complex set of lenses. If you think of it as one lens, it projects an image on a wall of sensors, in a plane of sensors. Right? So, for example, when you get yourself a camera these days, it tells you it's a 35 millimeter camera, isn't it? What does it mean? It has a receptive field equivalent to a 35 millimeter film. It is there, and it is filled with these pixels. They tell you it's 45 megapixels. What does it mean? Those are the receptors on that, right? Except that in cats and in humans and in mammals, it's a little bit more complicated. We don't fully understand how the signal propagation happens. We do know that this eye's reception is on this side and this eye's reception is on this side. There's a crossover right over your pituitary gland. And but at the end of it, you have a projection. Your visual cortex is way back here. Right? So you can imagine that something like this is happening. So when they looked at the cat's brain, they saw this happening. So then they asked this question.
Sugar is కొంచెం sugar వేస్తే
Nice. First, to be on again.
Class different on that.
Yes. So when we
Just a basic question of how this process works, intuition wise. So
Yeah.
in the cat's eye, the first the inverted image appears, and then the interpretation of that.
that is right. So that how does a cat perceive? So very much think like a digital camera. How does a digital camera know? Except the digital camera doesn't understand an image, but a cat will see in its visual cortex. It is as though it's a wall of receptors. Are we together? So different areas of the visual cortex or regions form the receptive field for different parts of the image.
So when does it know that it's a tree? Because the inverted image cannot tell it's a tree, right? So it has to.
No, it is. It turns out that in all our cases, we internally inverted back. Those things are an understanding of things. We do know.
Okay.
So guys, with this, the intuition that they got is, if we want to understand this image, what we can do is we can understand it a patch by patch. So for example, if I had a detector for a leaf, I could go over the detector. So imagine, and this is, by the way, this is just intuition. Don't take it too literally. Whatever I'm saying, don't take it too literally. Let's call it a leaf detector. Imagine you had that. You had a magic little box. If you put it in one patch of the image, you could tell whether that's a leaf or not. So what can you do? To see all the leaves in the image, you could scan all over the picture and tell where the leaves are. Does that make sense? Right? But then you could have another little filter that would detect, let's say, one was detecting leaf, one would be detecting maybe a swing from a tree. I'm just taking metaphorical examples, so don't take it too literally. That's not how it works. Right? So a swing. And then you may come to the conclusion that there are no swings in this picture. Something like that. Right? So that's a basic intuition. And then what happens is that if you look at the, so let's just look at the leaf detector. Whatever, let's say, the way you do that is, there are certain sensors or ways to do it. And there's a mathematical technique called convolution that helps you do it. It basically says, I know what a leaf is. Right? So let's take an example. Suppose you knew that a leaf looks like this. Right? And what you're doing is you're sliding your leaf looks like this. you're sliding your template. It's just like a stencil, a template. You're sliding all over the image, saying, how much of a match am I getting? To what degree am I matching? Does this make sense, guys? Right? I saw a really good match. This is a leaf. Okay. But you have one stencil, one template that you use all over the image. Now, let us say that in a very simplified world, all you had to do is detect leaves and swings, right? But then you would probably have, in a manner of speaking, two filters. One for leaf, one template for leaf, one template for swing. Am I making sense? And with that, you could go all over the image and you could come back with the answer and say, yes, there are leaves, but there is no swing. So far, so good?
So when you have that stencil, is it one whole leaf or you're detecting?
No, at this moment, in a metaphorical way, consider it to be a whole leaf, right? And so if you see parts of a leaf, you may say that, well, it's beginning to look like a leaf. Maybe let me slide it over a little bit more, right? And when you get a perfect match, so you will have degrees of match. Are we together? You'll have degrees of match. So that's the basic intuition behind something called convolutional neural network. Right? This word, and I'm obviously those of you who are very familiar with convolutional neural net, bear with me because I am, from a strictly formal perspective, I am deliberately wrong, and I'll tell you how. It's a convolutional, quite a mouthful, convolutional neural net. So this thing we are familiar with, but let's box this word in, convolutional neural net. Right. So what does convolution mean? Would somebody tell me? Any hands out here? What does the word convolution mean? Convolute. What does it mean? Contortions. No. That is one meaning of it. One meaning is that you contort and so on and so forth. But what other meaning there is to the word convolute? So it turns out it's a mathematical term. And it quite literally means, in our context, it means that you look at a local region and you search for something. Are we together? So there is a formula for, so suppose you have a function that goes like this. Okay? And suppose you have convolution that is just like this. So imagine a function, conv function, let me call it g of x, and then you have the green of x. So just go with the intuition, guys. This intuition is important to understand what we are talking about. This is fx. Now tell me, now once again, I will go from very wrong to less wrong to more precise answers, because it's important to get the intuition. Now tell me, what is fx, g, x, dx? If I integrate it, so forget about the integration. First tell me, just look at the product of these two. What do you think the product will look like in this region? Let's say at this point, what is gx? 0. So basically this product will be a take, and let me take a point C, let me pick a point B and a point, let's say, D. What happens at A and C? A, C, 0. What happens at B and D? This convolution function gx, it is, let's say that it is multiplying the value at B with a smaller value than the value at D, isn't it? So what is it doing? It's paying more attention to what's happening at D, isn't it, than to what's happening at B, right? So it is almost like it's a convolution. Now connect the dots, guys. do you see that this convolutional function, in some sense, acts as a receptive field? I want to look at only this little part of the function in one dimension, isn't it? And to look at that little part of the function, I can therefore bring in a convolution function, right, which is zero everywhere else, but in this little area, it is pronounced, right? So that is the meaning. And so this is convolution. To do this is to, well, I will, actually, let me just remove this part. This is convolution. Well, actually, now, this is what we call convolution between F and G. F being the reality, F being what the reality is, this part, reality, and G being conv function. That conv function, one easy conv function is e to the minus x, isn't it? Because it will look like this, the bell curve. It's a pretty good conv function. Another could be literally like this. It says, I have a square view, just this, you know, a peephole view of reality. So I will just see what is here with uniform emphasis, but beyond this receptive field, I'm blank. I can't see it. So that's a peephole convolution function.
So is it like the optics is focused?
Focused, exactly.
And then it's basically convexed on
that is
area.
That is it. So that's the concept of convolution. So now in our journey towards being more mathematically precise, it turns out that mathematicians will slightly scoff at it. The real thing is f tau g tau minus x d tau, right? So dx. So let me just put it like this. This is the real. So when I put the integral sign back, guys, ignore it for the time. Just observe the fact that we are focusing. What it means is that if I add up all of the function values, if I add up, so okay, integral is nothing but adding up. So if you look at this region where this has value, significant value, what will you end up getting by convoluting with the bell curve? You realize that you will get a value of the function, accumulated value of the function, that is in some sense focused on just this part of the function, isn't it? But it is not the area under the function curve, but it is sort of weighted down by how strongly you see it, right? So that's what convolution is. Now, the more technical definition of conv is this, but in computer science, in neural networks, actually you don't get anything by doing this tau minus x. You get the same thing. So you will see that mathematicians and neural networks people, they differ in the way they write convolution. The reason neural networks you get away with this simpler definition is because it turns out it works. There's no difference. You just save yourself a small computation step, right? So having said that, now that we understand convolution, what is this relationship of this thing to our stencil? Do you see a direct relationship of carrying a template and going all over the image? Here is my convolution for a leaf. I go all over for a leaf, right? You do that. And so what happened is, people, now the big question is, if I'm looking at the external world or an image, the world is filled with so many things. It's not just made up of leaves and swings, right? There are ladders, there are people, there are trucks, there are lakes, there are mountains. So you cannot have a filter for every possible thing. You see that, right? So how do you therefore recognize those things?
This is the same as space definition.
No, don't go there. Just follow the argument. Don't go into applications at this moment. Right? So just think of primitive objects, stones, things, right? So are we together, guys? I left you now with a puzzle. Does it mean that we need to, for every known thing in the world, and there's a practical infinity of them, I need to carry a filter? That wouldn't do, right? That wouldn't do. So what you do is you don't carry filters for leaves and for like leaves and swings, but you go one level deeper. You carry smaller filters. Like for example, you carry a filter for edge, vertical edge. What's a vertical edge? Let's say that this side is blue, and this side is green. Then what happens? Do you see the edge in between? The line, right? The edge. So you put an edge detector. You can have a horizontal edge detector. You can have a diagonal edge detector, right? You could have a corner detector, right? Corner detector. And so you first detect the primitives. And then what do you do with the primitives? Then you say, oh, now that I've detected the edges and things, I can put them together into higher order geometric representations. Are we together? So just to make it very simple, suppose you could detect a rectangle. What is a rectangle made up of? 4 corners and 4 edges, 2 horizontal and 2 vertical edges, isn't it? You could do that. So, oh, thank you. And that's one. You see the evolution, how you can synthesize, and we just created a higher level, a more abstract thing, or a higher representation, namely a rectangle. Now you can go, likewise, you can detect circles by, you notice that all of these things sort of add up to a circle. Little primitives are adding up to a circle. And so suppose and you go to the next layer, somehow you could magically do that. And to the next layer you go, and this is what you detect. Okay. Oh, sorry. Let me make it like this. Suppose you do that. You put it together. Yes, you're putting pieces together. And now what is it beginning to look like? Yeah, this is beginning to look like, and then suppose you have to do, and let's take a practical task. You have to tell what the object is, and the choices is it's a cat, it's an automobile, it's a house, right? Suppose you have to write a classifier between cat, automobile, and a house. Suppose you come across this. Are you at this moment in a place where you can make a reasonable inference? You can, right? And therefore you can create a classifier, an object classifier in the simplified view. And so what happens is you don't have, in the very first layer, you don't have such a thing as a leaf detector. But what you have are primitives, like for lines and edges and things like that, which in the next layer you synthesize to create a higher level representation and a higher representation and so forth, till you have enough of a higher representation that you can say, you can make an inference for the task that you have at hand. So this journey is the journey of using convolutional layers, many layers, a deep network to do that. And it represents one of the great milestones in our field. Now, the history of these filters is very interesting. The question remains, okay, what stencils do I carry? What templates do I carry? These templates are called filters. These detectors, think of it, those micro feature detectors, the templates. So guys, if you do that, no? If you had to, like, if I take a sheet of paper, let's say I take this sheet of paper, right? And on this sheet of paper, I cut out a shape. Let's say I cut out a shape like this. I cut out a shape like this, right? What can you do? You cut it out. You can just slide this thing all over your image and detect a leaf, for example. But here we are not talking leaves. We are talking about very simple filters. So people began to ask, what is a good set of filters to use? And before deep neural networks took over this problem, in the world of computer vision, there were many such filters libraries of filters that people would advocate for. They would say this library of filters is more effective than that library of filter. And many of these libraries, they were empirically established. People did it by trial and error, right? They knew that if we use this library, we can get this job done. And then the contribution that deep neural networks brought is that it asked this question that, see, we have the magic of gradient descent and back propagation. What if we did this? So now pay attention to what we are saying. If we take a filter and we say, learn the best templates, con filters. Learn it. Go figure out. I'll give you as many images as I can. Let's say I give you the whole ImageNet data set, hundreds of millions of images, right? Can you therefore use the task, let's say some task, image classification, house, cat, automobile, use this task to learn, have a process of coming up with higher abstractions. No, at each of the levels, guys, once again, may I request that if you are not speaking, please keep yourself muted. So we need to, so this is a question to ask, isn't it? Why can't we learn it by giving it an end task and saying, if this was the end goal you have to achieve, and I give you only 10 filters, what should those 10 filters be? Does that seem reasonable? Let it learn by back propagation. And that was the key insight. That insight that you can have learnable filters is the insight of a convolutional neural network. Yes.
So when you say you're telling it learn 10 filters, so it's actually creating those filters?
No, it will randomly pick some filters, try it out, then change. And you'll see the process now. You'll see the process now. Key insight. Yeah.
The filters, I mean, I'm assuming you have some pre-specified set of filters like edge or those.
No, you don't. And what I'm saying is, machine learning said that don't even have that. Okay? Just go discover what those, like I use the word edges and corners and so forth. It turns out that deep learning, when it learns something very close to it. Right? Yeah, but the statement that made is by machine learning is, hey, why are we making, see, it's a bias you bring in, right? I believe these filters are the good filters. How do you know? Why not let the machine learn and discover these filters on its own? Making sense? When you do that, that key insight makes it into a neural net that you train through back propagation. Right? So a lot about filters. Now, what does a filter mathematically look like? Let's think about it. Right? So I'll give you an example of a filter. Very simple 3x3 filter. And these filters are very small. So one thing about a filter is, what is it? It's a tiny patch. It's a tiny stencil. You swap it. You slide it all over the image, isn't it? Here's the stencil that will detect supposedly a leak or an edge or something like that. So let's take this. It is in reality nothing, because everything eventually has to be translated. Intuition has to be translated into numbers. Right? So tell me, what is this thing doing? 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1. Right? So imagine a gray scale image, right? Which had, suppose there's a patch of image somewhere here, and in here, in some region, you had a line, right? So let's take a vertical line. So everything here is +1, everything here is 0. Are we together? So imagine that you're taking this stencil over it. So 1, 0. So let me align it to one of the boundaries just for the sake of argument. Something like this, right? 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1, minus 1. What do you notice here? If you multiply the value of the filter with the underlying pixel value and you add it all up, at this particular patch, at this location, what do you get? 1, 4. You get 4. Does that make sense, guys? Why? Because here the background is 1, isn't it? And here the background is 0. So these minus ones don't count. Are we making sense? Now you can slide this pixel. Suppose this pixel was, this filter was here. What would it say? 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1, minus 1. What would be the total here?
0.
0. Right? Do you see? So what is it telling you? This filter, based on the total that it's getting on the convolution, is telling you what? You are on a edge. Because when you take it past this, once again, 1, it's 0. Do you see that? Right? So it rises from 0 to a high number and then falls back to 0. Therefore, locally, it is saying you're encountering an edge, vertical edge. Right? So that's what filters are. Con filters are, and a 3x3 or 5x5 are very popular. 5x5, these are the sizes that are quite popular for filters. Right? Rarely 7x7, but this is it. So this is a filter. Here, those numbers are defined. So you would say a vertical edge detector.
Asif?
Yes.
Sorry, in that example, in the left rectangle, why is the sum 0 on 1, 1? Because it's in a one region, right?
Yeah, because the background is, you're multiplying it by the background pixel. What is the background pixel? It's white. It's white in color.
Yes.
White, black. So 1 times 1, so it is, look at this, 1 times 1 plus 1 times 1 plus 1 times 1 plus 1 times 1. This is only in the first column.
Yes.
Right? Column 1 plus 1, 0 times 1 plus 0 times 1 plus 0 times 1 plus 0 times 1 plus minus 1 times 1 minus 1 times 1 minus 1 times 1 minus 1 times 1. Add it all up. Sum it all up. Sum is equal to 0. Do you see that, guys? No edge there. Yes.
So in this case, we're calling it an edge, and we're saying the edge is between a +1 and a 0, right? +1 on one
Black
side.
and white. Black and white.
Black
White
and white.
in grayscale. What is white? 1.
1, okay.
What is 0? What is black?
So in a color representation, these could be different numbers, but the same template.
The idea is the
still
same.
produce,
See,
right?
color is nothing but 3 different channels. One for green, one for blue, RGB, red,
yeah.
blue, green. Right? So you just keep 3 different channels.
So it may not just be a 0, 1 representation. It will be like some other number representation that would signify.
No. You apply the filter separately to each of the 3 channels. Right? Because you may have a green edge, but not a red edge, for example. Right? So you do a 3 separate analysis for each of the color channels. Okay, guys, are we understanding what a convolution is? Convolution filter is? But it begs the question, this one was a vertical edge detector. Suppose I say that the filters themselves are learnable. What do I need to do? Go back to this thing. See, what is it that I sort of by fear told you that this is the value? These values, right? 1, 0, minus 1. So what I could say is, we don't know. This is that particular filters F11, F12, F13, F21, F22, etc. Basically, it is nothing but a 3 cross 3 matrix of floats. numbers, decimals. Are we together, guys? And to the extent, now let me write it. It is something like, it's basically weights. These are the weights that you can have. But now observe the key intuition. The hyperparameter still is, how many filters do you use when you see an image? What you do is, suppose you see a tree. Well, let's go back again and look at a tree. You saw the tree, or rather a picture of the tree. The first question is, what's your filter size? 3 by 3, 5 by 5. People take odd numbers, and you'll see why. And so there are lots of little knobs to turn, hyperparameters and decisions to make, but we'll keep to simplified thing. Now, how many filters to pick? Because each filter is going to detect one feature, some feature. You don't know. I made it very intuitive by calling it leaf, then later on edges, but you don't know. You let the machine determine. Based on its weights, God knows what it is detecting, right? Because it thinks that is a good feature to detect. But still, you have the right to tell how many filters or how many features you want to detect in the very first, when you encounter the image itself. So you detect some filters, so you will end up with a feature map. Feature map that says that lots of features will pop out of it. Each filter will produce its own representation of what it found all over the image. Right? And that you do. And so now it's getting into a little bit technical, and I'll just say it now because it seems that many of you don't have. You go through a crucial thing called pooling. What you do is you take local areas and you just either sum up or average it or find the max of that or so on and so forth. Why is it doing? It sort of decreases the resolution, decreases the size of the feature map. Are we together? So a pooling process decreases the size of the feature map. So what will happen is, in some sense, think of it as a reduced size through pooling. Pooling reduces it. Reduces the size of feature map. The size of the feature map. Obviously, I'm not going through the whole detail of the CNN at this moment. It does that. But then you bring back the same filter. See, your filters remain the same, but the feature map has gotten smaller. And when you apply it, and this is the crucial thing to observe, guys, this is something very interesting. Now, in some sense, it is looking at a little bit here. So suppose you have a reduced image, reduced feature map. This tree becomes something like this. Now the same filter, when you apply, it is applying still to 3 by 3 in this reduced feature map, a filter. But in the original, it represents now a little bit larger area, isn't it? Initially, the feature map was applying only to this, but now, effectively, in the next layer of the filter, when you again apply the feature, next convolution layer, it has a little bit more global view. Are we understanding this basic insight? And those are the two insights we need, because we're not going to do too much of CNN. In fact, we are going to move past the CNN. But here comes a statement that is worth making. Given these two facts, look at this. We say that this CNNs, by design, have two inductive biases. What are those? One of them, locality, local. Right? One is the locality, means you detect very local features before you detect little bit more global or coarse-grained features. Isn't it inherent to the way the filters work? Isn't it? If you create layers out of filters. Right? So locality is one inductive bias. I hope that's very obvious to you, right? Little things that are happening here. From there, you build up to the truck, to the cat, right? So suppose you build up to this. Now you know it's a cat, right? And so forth. The second inductive bias that you have is a special form of transformation, equivariance, called translation. translation equivariance. Now I'll take questions in a moment, guys. So locality part we understood. It's built into the inductive parts. Right? The filters, you have convolutional layers one after the other, just like you had deep, dense layers. Each convolutional layer creates a feature map out of what it gets. Plus, the pooling does a reduction. It sort of reduces the size of the feature map. So therefore, in the second layer, when you apply filters, it will necessarily have a little bit less local view of that region of the picture. The receptive field effectively increases, isn't it? That is the first part. Translation variance is that, suppose you're detecting a cat. 1 second, please hold on to all your questions. I know a lot of you have questions. So suppose I have to tell in the picture, is it a cat or a dog, or cat or a house? Suppose I were to move this cat to here, right? Do you think it will make a difference? It will not, because it will discover exactly the same feature maps. It just so happens it will discover way below. The location will be different in the image, right? So it has translation. What happens is that the activations that it produces, the feature map that it produces, are the same. You move the cat in the feature maps, the location of that activation goes down. And then suppose you were to feed it logically into, let us say, some final softmax after feeding it through some technology, some more layers and sort of. Let's say that you do the softmax. What does the softmax care about? It will say somewhere in there is a big active information about a cat. It doesn't matter where it is, but it is. And this machine will then say cat, irrespective of where the cat is. You can even rotate it. You can do all sorts of funny things. It would still say that. Are we making sense? So this point is the translation equivariance. So now you realize that, and I'll summarize it with this. You say that CNNs have two inductive biases, which are reflective of the external world. The external world displays local structures that then aggregate into less local structures and finally to a global structure, isn't it? The second inductive bias also reflects real world, namely a cat is a cat is a cat wherever in the picture it is, right? So whether you see a cat on the roof or whether you see a cat on the ground, it's still a cat. That's how you think about it, isn't it? But what is needed for a cat to be a cat? The relative, see, if you work your way backwards from the final feature map of a cat to its pieces, what is happening is in there is the head of a cat and a body of a cat and the tail of a cat. So long as the relative positions are not mixed up, you're fine, isn't it? Right? It should be like that. But if the relative positions are mixed up, so suppose it becomes like this, right? And head, tail, and then another circle. It might not be attached, isn't it? Something like that. So in other words, relative features, relative location are preserved. That's all that is needed in feature map. That's all that is needed for it to activate and learn that it's a cat. Its absolute position doesn't matter. That's your translation equivalence. Translation equivalence is a special case of a transformation equivalence. You can have many transformations that it could be invariant of. Right? But generally, this is it. So now, what are the consequences of CNNs having this two inductive bias? It turns out that once you impose this inductive bias, which is very legitimate, knowing the external world, you don't need to make this very complicated CNN with huge number of parameters. There is a great simplification because the same filter goes all over the image, isn't it? And so you say that there is an effective weight sharing or parameter sharing because the same filter here, every single thing has its own weight, okay? But not in a CNN. So CNNs are generally much smaller in size, than if you were trying to with the feed forward network, it would be much smaller than that. So far, so good. Now,
So we are effectively saying the G of X is same for each layer.
each filter is a G of X. So that matrix is effectively a G of X.
Another question, so follow-up question, the matrix what is selected,
Yeah.
is it always to be a square matrix? Or is it
Yeah, there is nothing to be gained by complicating and making a rectangular matrix. So by convention, the field has always taken square matrices of odd sizes.
And also, when you talk about the filter itself is being learned, we start with some all zeros and then slowly learn, is that or all ones?
The question in the audience that is raised is, when you initialize a convolutional neural networks, do you set all the filter values to 0? No, you always randomize it. And I think you were the ones raising the question.
Yeah, so my question is a feature, you said feature map goes through pooling with the reduced feature map. So this feature map is what, whiskers, eyes, nose, or?
Different levels, depends upon how deep you are in the, see, deeper layers are looking at higher order features. Early layers are looking at just edges, corners.
And so what does reduced feature map mean?
A reduced feature map is just like, one intuition that I carry is take a picture, the same picture, and in your whatever Photoshop, whatever picture tool it is, just reduce its size. Right? So what happens? You lose some resolution. That is what pooling does. But it takes the local values and adds it all up. So what will happen? It is a form of smoothing, local smoothing that takes place, isn't it? That's what it is. Because you'll have to do that to reduce its size. You have to, in other words, you lose some information. And it turns out that that's a good thing. So guys, that is what a CNN is. CNNs are much smaller. Their great virtue is that you can train a CNN with far less data than you would train, for example, to the same level of accuracy, a denseness, or a MLP. I will say that. Computationally, they are very efficient engines. So for computer vision tasks, the field of computer vision, it has been the workhorse for many, many years. You send a letter to the post office with handwriting in it, most likely it will go through a CNN-based thing to convert it into a proper address. And the oldest one used was literally LeanIt. Okay. So now comes, so that's a good intro to CNN. Any questions on CNN? I think there's somebody there waiting with a question. Go ahead. Who is waiting with a question in the back? Yes, Prashant, and you also. Okay, one by one.
Why do you need to do a pooling?
To reduce, because what happens is, if we don't pool, the next time the feature map will not look at will look at the same local part of the image. It won't be able to zoom out at all. Do you see that?
It is not able to give a complete picture.
Yeah, it won't create higher order understanding of the image. Yeah. Right? So it needs to zoom out, and that zooming out is important. That pooling is important, because that's what it does. It's a good question. What it does is, you realize that this machine now, at each layer, after each layer of the convo, it has an understanding of the image at a different granularity, isn't it? At a different resolution, it understands it. And this, by the way, has far-reaching consequences later on when we are talking about architectures like UNet and so forth. We are going to revisit this topic quite a bit. See, common sense, right? Sometimes you recognize something if you really look at it carefully. Sometimes you need to step out to see the bigger picture of what it is. So having understanding of features at every level of resolution becomes a key strength that CNNs bring, especially when you add residual links. We won't talk about residuals at this moment. It's a topic about for Tuesday. So that is that. Yes.
So that whole thing again repeats and repeats, right? Like,
repeats. Layer after layer after layer.
Okay.
Yeah. And you do many. So for example, if you look at some of the older, so some of the CNN architectures, Look at ResNet. Those are the AlexNet, ResNet, or VGGNet, VGG16, and so on and so forth. You realize that the number of layers is increasing by the time you get to inception. Okay, I'll give you a homework. Find out how many layers are there in Inception V3, or whatever the latest Inception ConNet is. That should be a fun task, isn't it? Find out and how much there is in ResNets, and so forth. Yeah, go ahead.
So each layer is a different pool.
A layer is like the way you define it in this world is you have alternation between convolution and pooling. So one unit, you say one convolutional unit is convolutional filters followed by its pooling.
So one convolution is a sliding up that
across the image, to create its own feature. That is it. Right. So each filter will walk. This is a slide template. You slide across it. You come up with, okay, what did I discover? It's my feature map, my filter's feature map, and then you decrease the resolution.
So essentially, we're trying to get to a state where that filter can go on the image by itself and can tell me what it is, right? Instead of like the small pieces of the image, it can directly go sit on the image
at the final stage. At the final stage, because that has a more global view of what it's on. Right? And that's why this thing, you can see people often use the word. It's not so common these days, but people used to say this quite a bit more 10 years ago. But deep learning is representation learning. And you see that in very direct action. Each subsequent layer learns a higher order representation of the input, isn't it? It's very sort of directly there. So I'll summarize and give you guys, I know that it's time for a break. We took this digression into doing a very quick recap or maybe an intro into convolution. I apologize that we can't go any deeper because for that you have to be in the theory class. But basically, it is the maximum use of learnable stencils or learnable templates effectively to figure out what in the world is this image or understanding the image. You can use it for many things, classification, segmentation, and so on and so forth. But we'll leave that there. What is to convolute? Convolute is literally what I'm calling a stencil template. And a basic intuition, not quite correct, is if you simply want to say, suppose I had a template or a detector for a leaf, I could go all over the image and see if there was a leaf. Something like that. Yeah. That is the basic intuition, though it doesn't work at that level. You start with basic primitives, edges, etc., and then you work your way up. So that is convolutional neural networks. I hope you are suitably impressed because this is one of the powerful workhorses of the neural network architecture. It's one of the most powerful neural network architectures. And again, in the Tuesday class, you'll encounter this in great depth. With those words, I'll take a break. I'll stop this recording and we'll take a break. The break will be for 15 minutes.
Seems like intuitively more, I would say,